Hi, my name is Sean Bernfeld, and I'm representing Oberlin College at the Ohio 5 Symposium 2008. So at Oberlin, we're trying to develop a working frequency cone, which we hope to apply towards atomic spectroscopy. Frequency cone is the output of a laser in a special condition called mode locking. And basically what you get in the spectrum is a comb of frequencies that are evenly spaced. The nice thing about this comb is every frequency on it, every mode, can be designated by an integer mode number and two radio frequencies. The repetition rate, which is the spacing between each comb, and the offset frequency, which is the shifting of the whole comb from zero. The nice thing about having two radio frequencies represent every mode on the comb is radio frequencies are a lot easier to measure than optical frequencies. And we can reference these radio frequencies directly to an atomic clock and transfer all of that precision to our optical measurements. So first we start off with the laser. And the medium we're using in our laser is a sapphire crystal doped with titanium. And we place that in a bow tie cavity. We pump it with light at 532 nanometers, and it starts emitting light. And we get about 100,000 modes within our cavity. Our cavity is set up so it favors the modes locking their phases together and traveling together as a short pulse. And the nice thing about the pulse is, the shorter the pulse, the more frequencies that we have in the spectrum. And that's what we're hoping to get at. So once we have our laser mode locked, we have the pulse traveling around the cavity, and we have all these frequencies in the spectrum, we can look at the comb. So what we get is a series of pulses coming about a nanosecond apart, and they're about a femtosecond in width. And they interfere in a way to create our comb structure. With all of our combs, all of our modes on the comb nicely spaced and nicely designated by radio frequencies. So the other thing we need to do is now stabilize the comb. So we need to lock down the two free parameters of the system, starting with the repetition rate. And the way we do that is by shining the output of the comb on a photodetector. And each of the frequencies will interfere with its neighbors, and we'll get a difference frequency out, which is equal to the spacing between the comb, or between each mode, which is the repetition rate. And since each mode is interfering with its next neighbor and neighbors far and farther over, we'll get out integer multiples of the repetition rate over here. And we'll filter that out to just get the repetition rate. And then we'll mix it with the signal that is referenced to an atomic clock. And if there's any difference between the signals, we'll send that back in to a piezo, which will alter the length of the cavity, which alters the spacing between the pulses, which changes the repetition rate. We'll also lock down the offset frequency, if not. And that's a little more complicated. I don't quite have time to go over it right now, but it again involves trying to get out a difference frequency. We'll take light from one end of the spectrum and light from the other, and we'll double this, compare it to the two, and any difference between the two will be equal to the offset of the cone from zero. And so we'll send that back in to an acousto-optic modulator, which will alter the power of the pump beam. And due to the extreme nonlinearity of the system, that will affect the shift of the cone, the offset frequency. So the research we hope to apply the cone to is atomic spectroscopy. Next year for my research project, I'll be looking at a few of the transitions in potassium, and we'll utilize the versatility of the comb and the fact that there are a large number of frequencies available on it to look at multiple transitions at once. Specifically, I'll be looking at a 2-photon resonance and hopefully improving measurements of fine, hyperfine structure of potassium by an order of magnitude or two. We'll see what we get. But yeah, that's what I'm doing. I'd like to thank Jason for being my research advisor. He's off to the side. You can't see him on the camera. But, and everyone else who's helped me out with this. Thank you very much.